Hi, everyone. Thank you for coming back. This is Ben and Abdullah with OWASP Nova, and this is our last meeting of 2022, which is huge to say. We had a lot of great meetings across this past year, and we are thrilled to come back in 2023. But for right now, I want to just wish you all a happy, Thanksgiving for those of you who celebrate it, happy holiday, whatever you may or may not celebrate at the end of the year, and happy New Year in advance. So, Abdullah, do you want to say anything before we bring out Stefan?
No, it's been a great year considering, we just had so many ups and downs with the pandemic and everything. We're hoping for a strong close to this year and really looking forward to 2023 and what our chapter is going to do next year.
Yep. We have been talking about trying to do, in-person meetups. So that is something that we're bringing back to the table, and hopefully we can achieve it in 2023. So yeah. Anyways, we are about to bring on our guest, Stefan, who will be talking all things NPM and supply chain management. Stefan he leads the red team at GitHub, and he is a man of few words in terms of a bio. So I'm going to bring him on now. He's a man of few words in terms of his bio, but he has a lot of incredibly valuable information to discuss across our industry. I mean, I feel like every time you talk, here, AppSec, wherever, it's just a fountain of knowledge. So
I'm okay if we want to end this early. NPM supply chain is hard. That's the takeaway of it.
I got you. All right. Well, the floor is yours. And yeah, if you have any questions, please just throw them in the chat. I'll bounce back on and we can address them as you see fit, because we want to pick Stefan's knowledge as much as possible. But until then, it's all yours.
Ben, thank you so much. Abdullah, as always. So thank you very much, everyone. This is a pastiche of packaging, or understanding NPM with style, elan, and verve. I figured we'd do some background information, what you should be taking away from this, key takeaways. But really, I want to dive into what are packages, obviously within the context of NPM. What are registries? I think very often we talk about what these sorts of things are without actually necessarily defining that these are pieces of infrastructure, pieces of code, pieces of definitional things that we want to process, and tie them to specific concepts, tie them to specific file formats for here. And then maybe walk through a package lifecycle. We'll go through some of what can actually go wrong with packages. Again, specifically to NPM and what the deep dive was there. But in general, what you'll see across ecosystems, most of the things discussed here are very applicable to PyPI or Cargo or any of the other package systems out there. And then lastly, we'll just dive into some of the things that we've done, some of the things that we've seen, and we'll close out from there. So, as Ben mentioned, my name is Stefan, Steven, Ishtvan, whatever you remember. Really have no preferred pronunciation. I'm a staff engineering manager at GitHub. I lead the red team at GitHub, as Ben mentioned. Our focus, or our foci, the main areas that we work in, are adversarial thought, adversarial action against infrastructure and products at GitHub. So when a new product is launched, we may target it for various purposes, move laterally through it, etc. See what we can find, and then actually use it to break into other things, or just target it directly for itself and its own reasons. Personally, my interests are in programming language theory and logic, especially like program proofs, provers, that sort of thing. So a lot of the things that I do tend towards programming language theoretic approaches. You'll see in here that I built a parser for some of the work that we've seen based on the language I was using, but I tend to work in like compilers and theorem provers outside of work as well. It's my general interest area. So if you are to take away anything from this, I'd say there's probably these three things here. Packages are basically some sort of definition file or specification for what you expect to happen. For NPM, that's package.json. And then there's some stuff, whatever that is. It might be code, it might be binaries, it might be other configuration files, other packages, etc., that is defined by this specification that the package system installs when you tell it to. And then there's an install location. And we'll see as we get into it, there's a reason why I call out those three things. But for NPM especially, those three are incredibly important as you think about what a package is and where it ends up. And that the registries themselves are not anything special. I think very frequently there's a lot of thought that registries are this like magic place where all of this hard work goes on, and there's a ton of hard human work that goes into it. Curating the registry, making sure that it's not just filled with malware and things like that is actually a lot of work, and there's a lot of really great humans that do that work. But registries themselves are a very defined set of items and file types that actually make up those registries. And lastly, there's a ton of footguns. This isn't specific to NPM. All packaging systems have a ton of footguns. Just NPM does have some very interesting and specific ones there. Arguably the more important ones, I know very often when I give talks, I use words that people are not familiar with. So I figured up front, before it became a question, I would actually define what the three that I used are. So there's pastiche, which is like a style imitation, elan, which is the actual energy or enthusiasm, and verve, which is generally the vigor behind some sort of action that you're taking there. I know if you're taking anything away, those are the three things you wanted to. So why did I actually end up writing this talk? So this talk actually was an internal GitHub talk originally. So my unit director is Greg Ose. He's a great guy, and he was very curious to see what NPM's exposure was to certain things internally for GitHub, externally, and so he tasked Red Team, myself, with doing a deep dive into NPM and looking at what makes up NPM, what does the package system look like, what does the underlying structure look like, and then looking for what the normal attacker TTPs are. So looking what actors are actually doing, where they're doing these sorts of things, and how they're actually attempting to subvert the ecosystem for their own gains, and where do those things actually live? Where do they live in packages? Where do they live in the registry, etc.? And then look at the tooling that exists in the space and see if it's usable for us. The space has gotten much better since I initially looked at it. But originally going into it, it's like there's the dependency checks and those sorts of things. But if you were looking for health checks, there were much fewer in the space. And I'll talk about tooling later in the talk. So the background is really that we were trying to figure out what does the risk of NPM actually represent to GitHub, to the community at large, and specifically to the ways in which we use NPM and packages more broadly. So we own it, right? We own NPM. We wanted to know what the current state of affairs are, but more specifically, we wanted to actually understand what makes up the entire background and what is our current exposure. So one of the things that we did was like gain knowledge of and access to all of the package.json files internally at GitHub. So we've done quite a bit here to actually start scanning across our internal usages here. So when we were looking at what actors and attackers were actually doing, we were really curious about what you would see in the space, right? I think we could all conceive of certain things that would come out. We'd probably think of someone trying to access, authorized keys or known hosts, trying to do something untoward with the file system. What was very interesting, though, is as much as you could see these sorts of things, right? That like there's lots of name confusion. Attackers were obviously doing typo squatting. They were doing things to modify the install location, or trick you into installing from another location, or using like the actual npm as a cheap CDN. Most of these things aren't actually as easy to find as you would initially expect. Very often, especially in npm, a lot of npm is actually used for these sorts of system configuration tasks. So, for example, if you would think that a strong signal would be accessing Etsy, right? Someone doing something in Etsy there, it wouldn't necessarily always be a strong signal. You actually have to look for other signals in the noise or in the chaff that you're actually sorting through in order to find things. Now, this wasn't always the case. Obviously, anyone using burp collaborator in an npm package is almost certainly malicious, or they're testing things as a red team. But there's also only so many interesting names out there. So if you're familiar with the algorithms in the space, you may think if you're looking for typo squatting, all you would do is take Levenstein's distance or some other edit distance between two names, see which ones collide, and you would have a great list of typo squats. It's not actually the case. There's quite a few packages. And remember, NPM represents almost 3 million packages at this point. So whenever you were looking through, there are people actually actively, attempting to typo squat packages. They're attempting to typo squat other items within the registry itself. But it's not nearly as simple as just apply Levenstein, apply a few signals, and boom, you're done. It actually was much more complex than I initially expected, and I believe others have expected as well. There's really no golden road to geometry, and there's no golden road to determining where your attacker's TTPs will actually be. So the last thing that we wanted to dive into, especially as we were looking into this, is what is the existing tools in the space? I think we all know OS step check. We all know Sneak, and everyone else has their dependency checkers there. But there's so much more to the space. So we were really curious as to see what else is out there, what else is doing the sorts of checks that you would care about in the ecosystem in packaging itself. So to take a step back, there's actually a certain set of things that you care about with packages in general, right? You might care how much time a maintainer spends maintaining that package, right? You might want to look at the health of the ecosystem. Is it one person or is it 100 people? So that if the maintainer decides tomorrow that he's no longer going to maintain it, or he's going to, I don't know, turn it into a protest against a government policy, there's more people who can take over and can help to maintain that package there. You have good package health. Or you could look within the reputation of the system. One of the interesting things that we've seen is not only who is committing to a package, but who they've worked with previously. Doing friend of a friend graphs on folks is fairly interesting to see what's the actual reputation of the package, where's the package actually installed normally, and looking at honestly the network of the package itself. And then lastly, obviously we care if there's security vulns, but we also care how long they sit open. Are maintainers getting barraged with tons of tiny little vulnerabilities that aren't helping, that they're not fixing? Are they fixing things in 2 hours? Understanding the actual tools and understanding the actual health of a package are what we really need to be looking at when we're looking at packages. And for ourselves and our own consumption, right, as developers or as people who have to secure applications, we're really concerned about a few other things there. For example, with npm, and we'll get into this a bit later, you can leak internal package names, or you could pick up a package that you didn't expect because you're using an internal package and there's also an external package with the same name. Obviously, we always care about old packages. I think we've all dealt with Dependabot or other dependency alert solutions telling you that you have something out of date. But what is the actual implication? How transitive is that dependency? That's where we actually start to care and break things down. And lastly, the sprawl. I think we've all seen like software bill of materials, SBOMs, become pretty popular. But how many packages we're installing? What's the average number of packages? What's the average number of dead dependencies, etc., that we're installing as we look at our ecosystems? That's where it becomes interesting for our own package usage internally. So the space was not as robust as I would have liked, but there were definitely some interesting ones out here. Microsoft, specifically Michael Scavetta's team, works on OSS Gadget. OSS Gadget includes a whole suite of interesting tools in it. Like, so if you're hunting down for one of the things actors like to do is use base64 to encode their payloads. If you're looking for which packages have tons of base64 in them, OSS Gadget is great for that. It also has great breakdowns for health and reputation across the entire ecosystem of the package suites themselves. And what's nice about OSS Gadget is it's actually multi-system. So works on NPM, works on cargo, works on those sorts of things. I also forgot to mention here, Google has done a ton of work here with their OSS work, with their SLSA, and some of their SBOM tools as well. A ton of really interesting and similar work, honestly, to what OSS Gadget is doing. Some of the health things are specific to OSS Gadget, but definitely Google is also making contributions similarly here as well. Trail of Bits has worked on It Depends, which is SBOM generation. There's quite a few tools out there that do software bill of materials work. And it's definitely an interesting space. But this was actually something that we had looked at and considered. And then obviously for each of your ecosystems, there's going to be interesting things like pip audit, cargo audit, those sorts of things, which maybe aren't necessarily built into the ecosystem that you're using, but do add value for auditing. NPM itself has added audit directly to NPM as you install, but not every ecosystem has it built in. And so it's useful to know what your ecosystem provides. Like Rust, obviously installing the Rust sec tools like cargo audit are huge. The other thing too is I think there's also a propensity to consider known, vulnerable, and out of date as very similar findings or very similar issues. And in actuality, you can have an up-to-date package that also has a vulnerability in it. There's no new version to install, but that version does have a vulnerability in it. And knowing that via some sort of auditing platform or some sort of auditing tool is incredibly helpful as you attempt to determine your risk, or if you're a red teamer like myself, determine vulnerability for an application that you're looking at. So that was a lot of words, right? Let's take a step back. What even are packages? And honestly, each system is actually slightly different, right? They've made decisions for transitive dependencies, especially in different ways. So for example, in pip or Python, excuse me, if you go to install a package and it has a dependency on a conflicting package, pip will actually throw a warning or an error depending on how they conflict, and it may fail the install. Whereas npm actually adds to your node modules, and each package has almost an npm space unto itself, and they can use their internally vendored like dependencies there. But then you have the trade-off that there's huge bloat. One of the things that you see very often when you have a node modules directory is that it's enormous. I think the one that I was using internally was like 200 or 300 megs just for the tools that I was developing in order to originally do this sort of work. But for every system, there's basically very similar parts and very similar pieces for each. And here I'll just be talking about what we've seen in npm. So at its core, a package is just these three-ish things. There's some package.json which provides some specification. Really, what's required for npm is just a name, a version, and main. Basically, what do we actually do with this thing? What is the name of this thing, and what version of this thing are we on? There's package data, and ostensibly you would consider it to be JavaScript, but in actuality it can be anything. For example, I use ReasonML quite a bit. ReasonML, when you install the Node version, actually includes a whole host of binaries, and we'll talk about this. And then there's some location that holds the package. Now for npm, it's the registry itself, but in actuality, there's a huge number of places that you can install, and npm itself will actually attempt many of these locations. Most package managers have an analog of this, although npm has quite a few, and again, we'll get into that in a bit. So this is a fairly simple package JSON. It has a name in it. There's test package pastiche class. There's some version associated with it, which is 1.0.0. And then I define a main, which is foo.js, index.js, you'll see in here very frequently. It's a fairly common package.json for a application or for a library itself. Fairly simple. But a fairly normal one that you'll see, especially if you're not planning on distributing the application, is this. So you have the list of dependencies that you use. There's some associated versions. You can see that there's actual version restrictions on there. They're using semver. They accept up to certain versions, whatever it is, whatever that specification is. So this is a more reasonably normal package that you would see. Now, you may have noticed something. I said that there were three things that were required for a package, and then the one that I displayed on the screen had none of those three things. And that's actually correct, that the npm especially, but most packaging systems in general, are actually fairly liberal in what they accept. Name and version specifically are actually only needed to publish a package. So if you want to push something up to registry.npmjs.com, that's when you are required to have name and version. Otherwise, it's actually a free-for-all as to what gets into package.json. And there's a number of ways to actually consume packages in various different states, and there's various different ways that you would pull those packages from their various locations, and they may not have any of the information that you're looking for. So if you're an incident responder and you're trying to look at what is my node modules doing, or what is my requirements.txt doing for a Python application, you have to understand that the install locations are just as important as what you're seeing on the file system themselves. Because if an attacker controlled DNS, or they controlled a website that the registry was hosted on at the time of the attack, but not when you're looking, you can have a completely schizophrenic view into what the state of the package is on your system versus what the state of the package is on the registry. And then you also have to be mindful of very interesting historical trends. So my favorite one in NPM is that it accepts bundle dependencies versus bundled dependencies. And they actually have meaning, and there's specification for those. But if you're not paying attention, you may actually include bundled dependencies, which are effectively vendored ones, and you may miss the instruction to bundle those dependencies there. So understanding all of the locations and understanding the nuances is important as you go through and look at packages themselves. And then there are a number of fun things, especially in npm, where and we'll talk about the scripts object, but npm has a number of locations that it will run scripts from. But whilst they should be labeled, they don't necessarily need to be labeled. And so there's a number of nuances that you have to understand as you're looking through your package.json or whatever registry version you are, to pay attention and actually understand what the application does with that versus what you expect it to do. So in npm, there are three major types of packages, and these are associated with three major locations that they're installed. So We have unscoped packages, and if you've ever done node work, you know Express is you know, a router framework that is relatively popular. Then you might have scoped packages, which here we have a package that is from WooCommerce and it's their end-to-end environment. And then you might have private packages. Private packages mean that they're actually only available to named contributors, either individually based on a username such as mine, which is lojikil, or to an org name such as like GitHub itself or Microsoft or whomever there. So the actual packages themselves, as I mentioned earlier, can have anything within them, right? So when you're actually looking at a package here, I've actually split off my buckle script platform, which is very aptly named BS platform. But this is the platform that I use for working with Reason. And as you can see internally here, we have a bunch of executables, such as the Reason compiler and the Reason bundler itself. So packages they can live at 3 different locations. There's or multiple different locations and multiple different types, and their contents can be effectively anything. And so we have this situation, especially in npm, where the packages, and really what I want to expound on you is that the packages don't actually care necessarily what's in them. What they care about is getting the things that the package described to the right location that you specified or that the package specified from the right location that you or the package specified. And it's literally just some sort of specification and a tarball. And in fact, honestly, most packaging systems work in very similar ways. They have some specification file and then some zip bomb that they drop on you, and then they basically open on the file system. Now, where this is interesting is that these actually can trigger and run executable code, and we'll see some examples of that later in this talk. But there's a number of locations where we've seen actors, malicious actors, and we've also seen regular users use those scripts to their advantages to run certain things at certain times or do system administration tasks that can run in the wrong environment, like cause quite a bit of damage, or just generally not do anything that was expected because it was set up or meant for an individual place. And they're really similar in most packaging systems. Rust has solved some of these problems. Go does not have these sorts of problems. So if you're looking at like Go mod or anything there, you won't see the same sort of completely agnostic background of content, but very similar problems plague most packaging systems, or live in most packaging systems, I should say there. So at least if we say npm install foo, the install location is pretty well known, right? It should be extremely straightforward. Well, actually, npm PyPI or pip usually as you're using it, although you could use it via Poet or other ways. There's actually a hierarchy of where they look and how they resolve packages, and npm's is quite interesting. So in order, npm will try this suite of things to check where a package that you have requested should be installed from. So it will reach out to the registry first. If you have a scope, especially in a package, it'll look for a package and a tag, package and a version, because tags would never collide with versions there. It would never collide with a version tag, version range, etc. So there's quite a few locations, but where it gets interesting, obviously, as you can see, folders in here, a tarball file that's local, a remote tarball, maybe a remote Git URL, or in and of itself, very similar to Golang, a GitHub username / a GitHub project. And you can see there's a number of locations that could easily be confused, especially if you're looking at this after the fact, or you're looking at this in a state that is not necessarily the one that the developer or that the user who installed all these things intended. So the key takeaways from packages, and I know we're introducing, we'll build up to it, but a package itself is just some specification plus some general cruft. Usually that's installed via tarballs in some registry location, but they can be from virtually anywhere. And if you're responding to an incident, or you are attempting to attack a system here via dependency confusion or something there, understanding where the packaging system that you use installs or resolves packages from is incredibly useful for narrowing down the scope of either what had happened or what you can attack. And it's not unusual to see a ton of very different information stored within packages. And honestly, if I may, you probably want to disable execution when you're installing these. Unless you've audited them, you've done some looks around as to what they're actually installing, you probably actually need to play it on the safe side, look into your packages, especially in certain environments. You probably want to end up with doing builds and then pushing the resolved system and all the code as one gestalt, as one packaged up item, rather than doing an install for each environment there, if you want to be truly safe for these. So we've talked about packages, but where do packages live? Generally, for NPM, especially, or for Node more widely, it lives in a registry itself. And there's actually a specification for it. It's called the CommonJS Compliant Package Registry Specification. It's honestly just a web server that returns package information. In fact, for a very long time, NPM has been just a CouchDB server. There's effectively the registry itself obviously is it processes things, but when you actually specifically request information, it's actually a CouchDB that is returning most of that information. And you can set private registries. You can globally set a registry from a different location, and you can, on a per package basis, request that from another registry itself. Now, for red teamers or for those who think adversarially, I'm sure you can see where that's going. And in fact, yes, there have been instances of actors actually using per package registries as they're installing. So it looks like it when you do an audit of the registry, or the packages, I should say, excuse me, it looks like you've installed Lodash, but actually it's from some other host. And now you have to go track down what the state of that host was at the time that you actually install packages. So very fascinating suite of things to have to look into. So if a package is if a package just has package JSON, then a registry has registry JSON. Now, registry JSON is basically a superset of all of the versions of package.json. So if I pushed version 1.0.1, you would see here in the list of versions, you would see 1.0.0 and 1.0.1. And the changes between each version would be reflected therein. So the registry includes an additional suite of things. You can see here the person who published it, their email address, etc., and so on. Whoop. Helps to not flip through. But basically, the registry includes a large suite of things in this, including integrity information and other information that is useful for you, especially on Blue Team, if you're trying to see what you have on the file system itself. Now, there's obviously a number of interesting locations or entries within this registry JSON itself. There's the version information, which you can look back and see what version of things previously would have done. So, for example, if you were looking at version 1.0.1 and you wanted to see the scripts, the install scripts that version 1.0.0 used, you could request from the registry to see what the previous version had done and see what the install scripts were and compare the two. We do leak the user's email address. Please don't submit that to us as a bounty. We know it. We've seen it quite a few times. But it's actually included there in order for contact as well as for what the user provides there. But we also bump a number of items from package.json up into the registry. So you'll see as we split apart a package, you might see a version, you might see some description items from package.json. Those get moved up into the registry itself. And then the README is actually dumped into the registry itself, so that you don't even need to access the package in order to display it. But also, as folks responding to things or looking into packages, you don't need to retrieve any information to see what the README itself states. And there's also a ton of interesting metadata directly available. So for example, here we might see the tarball, we might see like how many files are contained within, as well as how large this package is once it's on the file system. Excuse me. And indeed, these are just tarballs. At the end of the day, the package system is a way for getting archives from one system to another in a way that includes all of the surrounding information. So, for example, the test package that I had pushed previously, there's simply 3 files in it. There's foo.js. If you remember back to where I said there was a main entry, that's the main entry there. There's the package JSON that we had previously seen. And then there's some markdown file to give a description of the package itself. These are registered in the registry JSON entry within the package.json, and then also within the file system itself. So if you look at this, there's a lot of interesting names that you come across. Like I mentioned earlier, if you try to do typo squatting work, or you try to look for interesting names, or if you look at bounties, you'll see quite a bit is actually already existing within npm itself. So when you allow users to select names, they're going to select names that might be interesting. For example, they might select users, right? There's a package on npm called users, and it's actually not a leak. There's no information there. There's nothing installed. In fact, it's a security holding package, meaning that it was interdicted by a security team who noticed it was doing something malicious. But what's a fun one is this last one here. It's actually just a single dash. So, I actually had deleted that, but we'll get into it. But there's a whole number of interesting naming things, but registries themselves are just a location to hold names, to store the metadata and store the tarballs. They generally use JSON, but they can use TOML or some other mechanism, and then enrich that data with things that we see on the registry itself from the package specification package.json for npm. And it's incredibly useful when you're tracking actors, you're tracking an incident, etc., to see who had done it, what maybe email addresses you should reach out to, what scripts were installed, what tarballs were unpacked. All of this information is stored within the registry itself. So if you tie it all together, there's a package.json, which might have a version entry, which might have some name that gets tied together with the tarball, which also includes the package.json and whatever other data you specify. And then there's actually the registry entry itself, which includes version information, the name, and then a link to the tarball itself. This is the actual order of resolution when you're looking through on how npm especially ties things together. So I when I originally did this talk, I was doing it for an actual life cycle to show what actually happened. We're not going to necessarily walk through creating an npm package. This isn't necessarily a class here, but I did think it was interesting to actually look through the life cycle. So it's actually fairly simple. For npm itself, it's just npm add user that logs you in, provides you with either a URL or with a very simple callback mechanism in order to authorize this version there. It can you just create a package.json with some name and some version. You run npm publish, and then you run away because you accidentally pushed prod information to npm, and then you have to reach out to trust and safety and ask them to remove something instantly because you just pushed a prod in npm in your first class there, and everything is now on fire. This is your life. You live here now. So it's actually fairly simple. And indeed, I just here for what we may have done. But as you look through the npm registry, there's actually quite a few folks who have pushed prod keys, who have pushed Slack tokens, etc., to npm, because it is actually deviously simple to package things up and publish them. As you can see here, it's literally just npm publish. npm does all the right things. It creates a tarball for things, grabs it, provides you with a bunch of SHA sums, etc., and then throws the package up on the registry for anyone to view and install with all their torrid voyeurism intact. So the interesting thing here is, as you see, a lot of this is based on SHA sums. So you'll see the npm notice SHA sum here. That's incredibly useful if you're checking through to see what actually is tested and what's actually installed in a specific install location. And if you're ever in the spot where you have to check npm or other registries packages, that is actually the value that you will check the tarball has on the file system itself. So for example, I've taken the tarball, I've recreated it myself, run a SHA sum on it, and I've actually gotten the same hash out as what npm used itself. Now, installing works much the same way, right? We npm I install, or npm install, I should say, test package pastiche class. Npm goes out, fetches it, checks that there's no vulnerabilities in my amazing package here. There's nothing there. And then if you cat the local package.json, you'll see the type of dependency layout that we talked about earlier, which is that there's one package installed, which is test package pastiche class. So the whole thing from start to finish is you can check registry.npm.js for whatever package name you're looking at. You can download the resulting JSON. I do this quite a bit, especially when I'm looking for an actor or looking for a specific set of TTPs or just interested in what a package does. Grab the package from registry npm.js. Look at what the actual JSON is there. Grab the tarball, do a quick SHA sum on it just to check that it matches what's expected, and then unpackage it into node modules or just use npm itself to install. Now, okay, we've gone through roughly what packages are. We've gone through roughly what the registry is. We've gone through information tying them together, the life cycle of packages, etc. What can go wrong with this? Well, as we all know, literally no one misspells anything ever on the internet. It's never mistyped, and every single piece of software that we consume and use is actually good. So we have a very interesting footgun here. And in fact, someone may have caught it earlier, but what's fascinating is that there's actually something wrong in my package JSON that I initially showed everyone here. And it was funny because I was actually going through how I caught this. I was going through looking at my own software in order to give this talk initially. And I was like, what is going on here? And there's an interesting file in there. So if you're not familiar with npm, when you install, it creates a file called packagelock.json, and I must have accidentally typed npm install package lock. I'd love to blame this on someone else, but it totally was me. And there's actually a package that typo squats the name, or just squats the name, I guess you would say, of a file that npm itself installs called packagelock.json. And all this package does is tells you that you probably did not mean to install packagelock.json as a package. Now, there's quite a few of these that actually, when you install it, they just say you probably didn't mean to do that. But it's funny because as I was going through this, I myself accidentally typo squatted myself by installing package lock.json as a package within my talk on typo squatting like packages here. So these have gained some very interesting packages. There's a package called Dash, which I showed you earlier. And at the time, Bleeping Computer had written about it. There was like 700,000 downloads. There is probably much closer to 800,000 or 900,000 now. And basically, what happens is someone is mistyping, or they are thinking that they're going to add some other flag to npm, and what they type is npm I dash, and the package itself is just an empty package. It looks like it was mostly an advertisement for someone's packaging software, and it does not actually do anything in and of itself. But there are over 700,000, over 800,000, whatever it is, installs of a package that does nothing because there's that many mistypings internally, because people use these tools and don't necessarily know what they're accidentally installing. So the other interesting thing is understanding a scoped package versus a GitHub package. Now, I don't mean GitHub packages as in the GitHub product, but I mean, if you recall the install locations, NPM will actually attempt to install from a GitHub repo. So if you type @logical/foobar, that is a package that references the logical scope and has a package name of foobar. Whereas if you forget the that means that you are looking for a GitHub repository that called logical with the repo name of foobar, which ostensibly should have a package named foobar within it. And whilst they are often one-to-one, they don't need to be. There's no requirement that those two match. And in fact, you could be installing a package that you in no way, shape, or form intended to install. And even more fun, if you leave off the logical, you leave a slash on there, /foobar will actually look for a folder on the current machine named foobar and attempt to install a package from there. So there are a number of locations that you have to be careful of, and you have to look for and make sure that those actually did not resolve at the time of install. Or if you are an attacker, if you're a red teamer, you have to look for these sorts of locations and see if you can squat them and race the installer to own those locations prior to an installation, and then you can get position on an installation itself. So the interesting one is, what does an actual malicious package look like? And this is a highly censored version, but this is what threat actors are actually attempting when they gain a position. This code is just testing what information is installed. It was part of one specific campaign, but basically the actor was using a collection of things to gain host name information, username information about the device that was running, some background on what the network looked like, collecting all of this together, base64ing it, and then either doing a curl request, or they were doing a DNS lookup, depending on what position they had. And it was going directly to Burp Collaborator in order to actually exfiltrate install locations here. So this could have been a pen tester. Obviously, we all only use Burp for good, but quite a few threat actors actually use Burp. They use Cobalt Strike and other pen testing and red teaming tools in packages, and this is the sort of thing that you'll see here. They're actually using the pre-install script, as you can see. So when you say npm I for install, it will actually run this prior to the install in order to ostensibly set up the environment. But in this case, it will actually just gain a bunch of information about the system it's running on and upload it to an attacker location. And in here, fascinatingly enough, the attacker was just base64 encoding their location. We do have actors who actually watch what we do. We we watch them, they watch us. It's fairly fascinating cat and mouse game. If you're ever interested in doing this sort of thing, volunteering for a registry and spending time on the like threat hunting team is fascinating. Because there's a number of locations that you can gain insight into what actors do, and it's fascinating to see the TTPs that they do here. So, so the takeaway is no one ever mistypes everything. Everything is perfectly fine. Um, there's no way that you could confuse the install locations. No one would ever forget an at the start of their package name. They would never drop a scope, and no one in any way, shape, or form would just go on npm and tell lies about what their package actually does. So before anyone feels smug that you don't use Node, you're not vulnerable to these sorts of things. This sort of thing happens all over the place. Rust just recently had a very interesting one where an attacker was typo squatting a decimal library, and they were doing some very interesting mathematical calculations in there and downloading a malicious binary. The install location was down by the time analysis started, but it certainly looked like the actor was looking for folks who would use a decimal library, run some things, download it, and it would unpack the second stage based on the calculations that it did in the actual install there. So very fascinating to see Rust actually attack there. And Python has been attacked numerous times. It's often in the news for very similar issues that we've seen here. Um, and honestly, it's going to be a problem no matter where you try to install named things that someone else can pick the name for. And for the love of all that is good, blockchain is not a fix for this. There are so many dependency attacks in blockchain. It's fascinating too because npm is very often used as the basis library for blockchain. So you'll very often see folks complain about a malicious dependency that attempts to swap the address where currency goes. So they attempt to swap the address of an administrator so that they can actually use a dependency attack to move laterally into a cryptocurrency itself. And obviously, blockchains just sign whatever you tell them to. They don't necessarily prove any provenance or other information about it. They just are a very expensive proving system for hashes there. So it in and of itself is not a fix for dependency attacks here. So what can we actually do about this, right? This talk might come across as like, wow, there's a lot of complexity here. There's a lot of things to be done, but what can we actually do? Well, you can honestly parse everything. I'll show you in a second, but you can actually rip apart all of these formats. You can rip apart all of these packages and actually attempt to understand what's going on behind the scenes. You can use tools such as OSS Gadget and whatever your favorite dependency system is. You can actually reach into your packages, understand what your dependencies are, and reach into what the health of your system is, and try to understand what the software ecology, the software composition that you're using can really or you can understand these sorts of things just by using a few tools and really your understanding of what your application should be doing, should be consuming, and should be using. And then you can keep in mind where malice lives. There's quite a few places that npm itself will actually run a script from. As I mentioned earlier, it will look into the scripts object and will execute many things that are in there. There are ways to call scripts even if they are not one of these named ones. You'll see actors do this often, but the big ones are pre-install, install, post-install, etc. And getting a sense of where your package system runs scripts from or runs its build system from is always incredibly useful. And then understanding where scripts are, where source code is included and used locally, and where source code is downloaded from will always help you to understand actually where malice can be injected into your system, where malice is consumed, and where third parties may be able to influence what's going on in your local application. Now, I mentioned this earlier, but I was using a language called Reason. It's a dialect of OCaml. It compiles to OCaml. It's one-to-one, not one-to-one, but it is roughly transpilable to OCaml on a one-to-one basis. But Reason did not include a nice JSON library for both Reason Native and for Reason Web. So I actually wrote a custom JSON parser called RoseJSON. It's relatively performant. There's definitely a few things I could do with it, but it allows me to write code such as the following, which is actually the code that I use for checking for malicious scripts or checking for scripts that have suspect strings within them. This is from the code base that I wrote to check all of the package.json, grab all of the files that we've seen in there, and then check if any of the dependencies themselves have suspect strings. This is what it roughly does. There's obviously more code to it, but you really can parse and wrestle with all of these packages, and I implore you to do so in order to actually understand what's going on. And that's it. If you want to reach out to me, I blog. I've been trying to blog much more with pandemic at lojikil.github.io. I am on Mastodon. I will not say tooting, but I do use Mastodon there. I'm Lojikil on Mastodon, Lojikil on Twitter, and you can look at my projects on GitHub itself. Ben, you did not interrupt me, so I presume that there were no interstitial questions, but I don't know if anyone has questions here at the end.
Yeah, certainly. I'll keep that. I'll keep your slides up there, so if anybody has any questions, they can ask. Yeah. Oh no, sorry. There is a question now. Mitch is asking: are there any attempts to introduce signatures and validation policies on signing in the npm ecosystem? He's seen SigStore for container images in Python.
Yeah. So SigStore is great work, right? In fact, my previous company, Trail of Bits, has done quite a bit of work on SigStore. It's great work. CNCF is obviously moving that direction. It's something that we definitely have considered, and it's something that's boiling in the npm system. I suspect sooner rather than later it will be part of the system at large.
Cool. Yeah, thank you. I don't think there were any other questions. The only comments that were some of my slightly sarcastic notes. Basically, when you were talking about the naming conventions, I was saying that I'm glad there's no Bobby Tables in there as a name.
Yeah, there's definitely quite a bit in there. In fact, if anyone wants to do a deep dive, it's quite hilarious what some of the names are that you'll see in npm and in Python and Ruby. It's quite telling. I will say npm size works against it here. You definitely see a lot more colorful names in npm just due to the fact that there are 3 million packages instead of the 300,000 or 400,000 that you see in Ruby.
Mm-hmm. Cool. Well, yeah, thank you. This was an extremely informative talk, and we have some tools and some considerations for me to look for, namely typo squatting, to make sure that everything in my environments are secure, and I have something new to look forward to in my tool suite when I'm assessing the application. If there are any questions, again, your information is up there. And thank you, Lojikil, for coming in and talking with us. This was really, really fun and definitely informative. And thank you, everyone out there, for watching us, whether you're watching this live, whether you're watching on repeat. Thank you. And we hope to see you again in the new year. And I wish you all a happy end of the year and whatever holidays you celebrate between now and then. So take care, everyone.
Thanks, everyone.